My name is Frank Jas. Thanks for coming. Thanks for taking the time out of your day to spend some time for this talk that I'm going to give. The subject is going to be cyber detection, threat detection, and some different techniques, compare and contrast different ways of detecting threats, some of the pros and cons of those techniques, and specifically talk about machine learning and how we're applying machine learning techniques to detecting the latest threats that you find out in the malware landscape today. So first, a little bit about myself. I'm currently with Juniper Networks, where I'm a distinguished engineer. Before that, I was, I don't really know what that means, by the way. Yeah, they have all these grades, so now I'm a distinguished engineer. Before, I was the CTO at Cyfort, which was acquired by Juniper last year. And there I was one of the early employees responsible for building a lot of their technology, specifically their detection technology, which was focused on behavioral detection. And one of the pioneering things about Cyfort was, which was founded by Ali Golshan, was to combine behavioral telemetry with machine learning. In other words, look at the behaviors of a piece of malware or an object and apply machine learning to that to do detection. And we were one of the pioneers in applying that and productizing that. And it's based on that experience. That's what the talk's basically about, is the various things that we found while trying to operationalize machine learning in a very practical kind of setting like threat detection and incident response. So I'm actually a systems programmer. I'm not a data scientist, although in building these systems I had to dig back into my grad school days where I studied machine learning a little bit and refreshed my understanding of that stuff. So I can give you a certain level of depth and really a more pragmatic view on this topic, and I'll do the best to answer the questions you have about any more detailed theoretical underpinnings of the subject matter. And by the way, if you feel free to ask questions throughout the talk. I'm happy to answer any specifics that you want, that you feel some interest in. So don't hesitate if you have the courage to raise your hand in front of all these people here. All right. So machine learning. There's a lot of hype. There's a lot of hype surrounding artificial intelligence. Artificial intelligence has gone through different periods of hype and then AI winters, as they call them, where the hype doesn't pan out and everyone loses interest and no money flows in and like that. And right now, I think we're in a hype period again. And there's a lot of different articles that you see in the paper. IBM Watson has done some amazing things. Google and some of those sorts of companies, Facebook, are doing some really interesting solving some really interesting problems, some hard problems that if you ask people from the 80s and 90s, would you be able to solve this? No one would have thought that they could have done this well. But the reality is really that there are no cyborgs. We can do some good natural language translation from one language to another. There's some good facial recognition software, but it's nowhere close to real conversational kinds of and thinking kinds of machines. The reality is that machine learning is really statistical mathematical techniques. It's looking at points, data sets, and trying to basically fit curves to separate those points into categories. And basically, most machine learning solutions that I've looked at are typically always what they call binary classifiers. So you have a set of points and you're trying to separate them into two groups. And that's the problem. And so there's a lot of different math that you can apply, a lot of different techniques that you can apply to separating these points into two groups. And some of the math isn't as new as they'd like you to believe in the popular press. Like, oh, this is brand new stuff. Some of the best techniques come from statistical techniques that were pioneered in the 20s, in the 60s. Deep learning, which is one of the big buzzwords these days, is based on an approach that was first thought of in the 40s. Some of the early algorithms were developed in the 70s and 80s, and it's just recently that they've been able to take it to another level. And all of a sudden you get some results out of that technique. So it's all math that's got a long pedigree and That's the basic problem set that we're trying to solve, that we're trying to apply to this problem. Now, what's the problem domain? The problem domain is computer security applications. And the basic problem that we started with at Sci-Fort and now at Juniper with our product JTP is, given a file object, is this a benign object or is this a malicious object? Now, file objects come in all kinds of different ways, different pathways. Most common today is via email vector, right? You get an email with an attachment. Is that attachment malicious or is it benign? A lot of malware takes multiple stages to infect your systems, and the first step is maybe that email attachment. But then the second step is you open that email attachment, it really only has a part of the exploit or the attack, and then multiple stages then get downloaded off the net. So you also are going to see objects flowing through your network devices like your firewalls and like that, and you can also inspect that traffic and extract objects from that. You get an HTTP download with a certain content type, you pull that out, and then you try to see, is this thing benign or is it malicious? So that's the basic problem that I'm going to talk about today. You can take these techniques that I'm going to discuss and apply them to other kinds of threat detection, like a really popular kind of threat detection or a really needed type of threat detection is command and control detection. So there's different phases of malware exploit. The first one, or a malware infection, and there's a kill chain that's really borrowed from the military. MITRE Corporation came up with this taxonomy really of steps. And the first step is the exploit step, where your device, the initial phase, and then you have a download or infection step, where it pulls down more things that infects your machine, and then the last step is the actions on objectives. And typically the command and control connections happen at the very last stage of the kill chain. And the kind of detection that I'm talking about really is focusing on the first stages of the kill chain, because that's where those objects come in. Right, so, but the command and control detection is also really important to try to detect, because those are the attacks that have succeeded in getting through everything, and those are the ones that people would like to know about most of all, really, because they're the closest to actually doing damage. But it turns out that's one of the hardest problems to solve, because command and control can hide its telemetry in so many different ways that it's difficult to apply these techniques and get a signal that you can actually operationalize. And so that's another thing that I'm going to talk about. Is there's one thing about getting some detection of a particular malicious object, and it's another thing to operationalize it so that you can have an operations center where people are watching this telemetry coming in and responding to these signals effectively, so that they can actually respond and then take action in response to clean up or mitigate the infection. All right, so what are some of the traditional approaches? So let me pause there for a second and see if anyone has any questions about what I just said. Okay. So there's a couple of the traditional techniques for detecting malicious objects, so we'll focus on that subproblem, involve three different kinds of inspection technique. The first and probably most common is static detection. And that's what most antivirus engines that are running on your laptop are using to do detection. And that's also what most network devices are doing to use detection to detect whether or not the incoming flows are malicious or not. And there's a very good reason why those devices are using static detection, is because it's fast. And by static detection, I mean you look at the content of the object, just the bytes of the object, and you make a determination based on those bytes whether the thing is malicious or not. And a computer is really well set up. There's a lot of great algorithms for pattern matching, regular expression matching of all different kinds. So it's fast, which is important if you're sitting on a network device and someone's connecting up to some popular website that they want to look at, you only have milliseconds to do that inspection, maybe a tenth of a second to do that inspection before the end users are going to start complaining, hey, why is my network connection, why is Facebook not loading fast enough? So similarly on the endpoint, on a laptop, you can't consume too many resources to do this sort of detection because people are doing work. I don't know how many times I've been sitting on my laptop, all of a sudden the fan starts spinning and everything slows down and what the heck's going on? I look, oh, McAfee is doing a full scan of something. I just have to wait until it's done. And I know a number of people will say, well, let's just turn that off right now because I want to do my work. And so that's one of the main reasons why you don't have a lot of resources or time to do that kind of detection. The great thing is it's fast, and because it's fast, you can use it to prevent attacks. You can actually detect things as they're coming in or before someone opens them, and then remove the object or prevent the network connection from happening. And that's the best kind of detection or solution, really, is to prevent the thing from coming in to begin with. What do they look at? Well, they look for patterns of bytes. A lot of the bad guys, they know this, so they do something called packing, where they take the malware and they compress it or they encrypt it with a really not military grade encryption or even consumer grade encryption. It's just basically a compression technique to jumble up the bytes so that the patterns don't really make any sense anymore. So what the AV then has to do is they first have to unpack the object. That takes more time, so that gives the bad guys a chance to get through. And they'll repack the same piece of malware with different schemes, and so that the same piece of malware you might be able to download, 4 people downloaded from the same site, you might actually get 4 different sets of bytes, even though after it's unpacked, it's all the same thing. So it's really fast. What's the downside to static-based detection? Well, it's based on signatures, typically. Signatures of bytes that they find in the content, which has an interesting implication. And that implication is that they have seen this piece of malware somewhere before so that somebody can craft the signature for it. See what I'm saying? So what the AV vendors have deployed are these massive honeypots. In fact, all their AV endpoints sort of act as a honeypot in a way that all the objects that they see on any of the endpoints that have been deployed on all their customers can actually collect file objects and send them back to the mothership to collect new objects, and then they take those into their lab and start sifting through them. Is there anything bad in here? And then if there are bad things, they'll create new signatures and push that out again. Interesting story about that. I don't know if you're aware, but Kaspersky now is not very popular with the federal government as an AV engine. And the interesting story about that is the reason why that is that they feel that Kaspersky was the leak through which the latest NSA toolkit got exposed to the Russian government. And what they think happened was that an NSA contractor took this toolkit home with him, which he wasn't supposed to do, but just to work at home. It wasn't, planned thing. But Kaspersky, running on his laptop, said, hey, these are interesting files. I've never seen these before. Well, let's upload them. And so they went up into Kaspersky's cloud, where they think someone in Kaspersky, who was working for the FSB, the Russian equivalent of whatever the KGB turned into, looked at these and said, wow, this is really interesting stuff. And that's how it got out. And so after that, they said, we can't trust Kaspersky anymore. So no Kaspersky is allowed anymore on any government equipment. But that shows you this collection capabilities of one of the ways that they upload interesting samples and then generate signatures for it. Another interesting example of this case of this lag of detection is WannaCry, which hit last year in May. And it did a lot of damage in Eastern Europe, and specifically in England. The National Health Services got hit pretty bad with it, and it's still sort of circulating around today. And every once in a while you hear somebody getting bit by it again. And this is a great example of the lag in AV detection, because it got, National Health Services, all their computers have active AV running on them, but it got through all that stuff. And why is that? Because this was a brand new piece of malware that everyone's attributing to North Korea, but it was completely built from scratch, so no one had signatures against it. And so when, we woke up on, Thursday morning or Friday morning, I forget what it was, my phone was texting up, did you see what's going on? So we jump on, and we get some of these samples really early because one of our guys has got a lot of connections, so we can pull these samples out. So we got some of these samples, we threw it through our detection engines and we could detect it. But if we went on Virus Total, where all the AV engines were sitting there was no detection for these samples. And that was even 8 hours after it hit Eastern Europe. And we kept checking back throughout the day. And it wasn't until over 24 hours later that the first signatures and the first AV engines started to catch these samples. And so that's sort of the window that malware has, if it's brand new, to get through. And so that's really the window that we were focused on trying to close down. How do you close down that window so that you can detect malware without having seen it before? It's brand new. And so the way to do that is to look at its behaviors. Because ultimately, that's what defines whether it's malware or not. Does it behave badly? Does it do bad things? It's not what it looks like that's important, though that's a good proxy a lot of times for malware, what patterns it has in it, but whether it behaves badly. And so that's what we focused on. And what you do in order to catch malware using its behaviors is you let it run. Well, you can't let it run on the actual end user's laptop or in any meaningful infrastructure. You have to put it in a sandbox where it can't do any damage. And so you run it there, and then you collect a whole bunch of telemetry about what it's been doing. And then that telemetry, then you can use to do detection. Now, how do you use that telemetry to determine or convict whether something's malicious or not? Well, you can look at the obvious things. Does it try to install itself in certain directories? Does it try to kill the AV engine? Most benign programs don't do that. Does it try to send a lot of data out? You can look for that. Most benign programs don't do that, or some do. You can think of, remote backup tools would do that. But there are certain kinds of IOCs that are commonly associated with malware, and you can basically score the malware based on how many of those things it does, and then if it reaches a certain score, then you can convict it as malware. And so there's these certain behavioral signatures, and the way it really works in practice is that the vendors of these kinds of solutions, they'll detonate a piece of malware in a sandbox, they'll look at its behaviors, and they'll create a behavioral signature, a set of behaviors that are unique to this particular malware, and then they will encode that signature, and so then if they ever see something else behaving badly in this same way or doing these same behaviors, they'll say, oh, it's the same thing as that program. And that way you get around this whole packing problem where all of these things have all their bytes jumbled up, so there's no signatures that you can apply, but once they unpack and start running, they all run the same. And so that way you can catch that sequence of actions, and those are behavioral signatures, or this counting thing is called a Bayesian scoring technique for reaching a threshold and saying, yeah, it's done enough bad stuff, let's call this malicious. And so the benefit of behavioral detection is that it can catch unknown samples. Because WannaCry, in the end, started doing bad stuff. It did the same kind of bad stuff that everyone else did. It just did it in a new way, so no one had signatures for it. And so you could catch it because it did the same kinds of bad things that all malware typically does. And so you can catch it. The problem is that it takes time. Because you have to run it, watch it, collect the behavioral signatures. How long do you run it for? A minute? 4 minutes? What? So you have at least that much time to take to do the detection. So you can't put this in a blocking position on an AV engine or on a firewall because it just takes too much time. So there's pros and cons here. But you can catch zero-day malware, malware that's never been seen before. And so what we did is we took this behavioral data, we took some static indicators, Like if you know about Windows executables, the PE32 file format is the Windows executable file format. It's got different sections. You can count the number of sections. You can calculate entropy of each section. Those might be interesting. So some signal file size, some static indicators. And what we did is instead of using some sort of behavioral signature that our malware reversers would create after watching it run, or counting up known IOCs, we would take all those signals and give them to a machine learning classifier and let it make the determination about whether this was malicious or not. And after we do the detection, then we'll go up and look up some reputation stuff. We'll look up and see if anyone else has seen this before, because chances are it's not a 0 day. Most of the time it's not. And what the customers love to see is, yeah, you caught something bad, but what is this thing that's bad? Can you tell me something more about it so I can estimate the risk? Is this adware? Or is this a known banking Trojan? Or what is this thing? And so we'll look it up, see if anyone else has seen this thing, and we'll be able to add some context to the detection that way. So what are some of the benefits of machine learning applying to behavioral detection? Well, this is subjective, but in my opinion, one of the most interesting artifacts of this kind of detection is that you can now detect malware based on what I call indirect indicators. And now what is an indirect indicator? Like a direct indicator would be like killing the AV engine. An indirect indicator would be scanning to see what processes are running on the system. An indirect indicator would be check what version of the OS is there. An indirect indicator would be allocating memory in a certain way, allocating a big chunk and then setting the execute bit on it. And it turns out that, there's some other ones I can talk about as well. It turns out that machine learning is really good about taking these weaker signals, because just scanning for processes, that's not necessarily malicious, right? Allocating memory in this other way, that's not necessarily malicious, but you take a bunch of these weak signals or these indicators and you can take a lot of them, and combinations of them definitely do end up being more likely to be associated with malware than not. And what machine learning is really good at is taking signals and combining lots of them together and inferring from the combination whether something's malicious or not. So we can collect hundreds, thousands of behavioral indicators, and the machine learning is able to sift through that and figure out which associations are more likely to be associated with malware and which ones aren't. And some of the results are pretty surprising. I only found this out after watching the classifiers run on samples and wondering, how did it figure that out? What's it looking at? And over time, you sort of get this sense that, hey, look, they're combining this information in ways that we would never think to combine, because they're able, machine learning is able to find the inferences between many more dimensions than we can hold in our head. And so that's how it's able to do that. Another great example of this is like the difference between looking in a window and breaking the window. Like if you're trying to break into a car, break the window, that's a direct indicator. But a lot of times before someone's going to break into the car, they walk by the car and they look in the window. And then they might turn around and look in the window again. And then they'll do this, they'll look around. All right, machine learning would probably catch it based on that, as opposed to a real behavior signal. Interesting story, I was listening to a radio interview with an ex-New York City policeman who had written a memoir, and he was an ex-undercover cop. And the way they would go about catching bad guys is they would sit in a yellow cab and they'd drive around New York City and they'd find bad guys and arrest them. And well, how do you do that? You're just driving around New York City. If you've been in New York, I mean, there's tons of people everywhere. How do you pick somebody out and just, well, we pick somebody out and follow them. And how did they do that? Well, it says really, really easy. Most people are just going about their business, walking along, going someplace. The bad guys are watching the other people go about their business. And so they just look for somebody who's watching the other people and then follow them. And that would be a really successful technique. So that's an example of an indirect indicator that they had figured out was a really good predictor of maliciousness. The other great benefit of indirect indicators is that they are difficult to disguise. Malware typically has to look around a little bit first to figure out where it is and whether it should do certain kinds of defensive behaviors or not, and what it's going to do next. It's really hard to disguise that basic capability. And a lot of times we can detect malware not just on that kind of stuff, but like what kind of functions it calls. It turns out that the patterns of functions that malware uses fundamentally different from benign programs. And I think, this is my theory, I think it's based on the fact that if you look at the way malware's written, it's all written to really low-level APIs at least for Windows, low-level Windows DLLs like nt.dll, user32.dll. They're just programmed right to the bare metal. The ZW functions, they use those a lot. NT functions, they use a lot. Benign programs, if you look at that stuff's written, it doesn't use that low-level stuff. It uses Microsoft foundational classes. It uses .NET, uses higher-level abstractions. And when you call functions using that, the patterns of function calls down below are fundamentally different. The frequencies, the types of calls, and so it's actually able to pick up the programming tradecraft of malicious programmers versus benign because of that difference in abstraction layer. So it generalizes really well. In other words, somebody comes along, writes a different style of malware program, but uses the same types of programming techniques, the same kinds of memory allocation patterns, and et cetera. A lot of times we can catch it just based on that alone. So it's hard to disguise that and armor against it. A couple of other benefits is that the classifier, the effect of what it's trained to classify, what it classifies well, depends on the training set. And so, for example, adware is a great example of a type of malware that some corporations, some organizations are interested in detecting, other organizations could care less about. For example, we were selling to Baidu China. All this stuff that we caught, they said, oh, we don't care about that. No, that's just, people use that every day. No, what? Those are like browser plug-in things. They said, no, it's just, everyone's inside, just ignore that. So, but what we could do is quickly train a model and give it a sample set where we don't label adware as malicious. And so when it's not labeled as malicious now, it'll ignore it. And so we can just quickly turn around, focus the detection on a particular area. We can also change the sensitivity quite easily simply by changing the slider a little bit, and that changes the detection sensitivity as well. So we can adapt to the environment a little quicker than you could if you weren't using machine learning. And so what does the detection pipeline really look like for the JATP product? Well, we have a bunch of collectors that look at all these input vectors where malware can stream in, like email attachments, web, east-west traffic within your organization, like SMB traffic, file flows that going back and forth. And we send that to a centralized core, which is a fairly beefy box, where we do all the behavioral analysis. We detonate the object, we run it, we watch what it does, we take those signals, we translate those signals into a form that the machine learning can accept, we run the machine learning classifier on it, and we generate a detection. There's also some mitigation and enforcement capabilities that are built in. We can do some verification stuff, we can take some context from the environment, some other log data, to add more context to the incident responder so that they get the detection, they get a whole bunch of other context sitting around it as well. So how do you actually go about building a machine learning classifier? Well, in machine learning, really the data is the key component, the training data. You need to have a good data set to train the models on. And so how does that work? For the file category, for the file example, you have a bunch of files that of a particular type, like all P32s, executables that is, or PDFs, or Word docs, and you've got a set of those. And that's your training data. Then, from those files, you have to get features, like example of a feature is, did it call NT-query system information to enumerate the processes? Did it open a file in the temp directory? There's all kinds. Did it allocate, what's the average memory allocation size? That's a feature. Then you analyze and clean that data. And so for each feature, you're going to get a value. And for a lot of the data that we have, it's yes or no. Did it do this or did it not do this? So that would be a value 1. What's the average memory size? That would be this value. And that would be, whatever number of bytes that was. And for each sample, you'd get a value for each column. And each column has a particular semantic. Like this means it did NT-query system information. This means the memory size. This is the file size column. And so you might have several hundred columns like that. And so you get basically a vector of values for each sample. And that's the key step. Taking your sample data, transforming it into a vector. And what is that vector then? What's one way to represent a vector? As a point in an n-dimensional space. So you've just transformed your problem from figuring out whether this file is malicious or benign into the problem of creating a curve or a surface in an n-dimensional space that separates the points that are benign from the points that are malicious. And so that's the key conceptual framework for just about every machine learning problem. Take your data set, turn it into a vector, where each position in the vector has the same meaning for each sample, because otherwise the machine learning can't compare values along that dimension. And then there's different techniques for creating this surface. And the training data is probably the most important factor in the success of the model. The training data and how you map that data into a vector. So let me pause there for a second.
I have a question.
Yeah.
How do you actually go about selecting the sets of data that we use to train models?
That's what they call domain expertise.
Okay.
You have to be familiar with the domain, like the security domain. So in this case, it's the domain of programs, and malicious and benign programs, and looking at the behaviors of those programs and trying to figure out, would this behavior help me distinguish between the benign and malicious program? And so take some understanding of what malicious programs do that benign programs don't do, or vice versa, to try to see, let me get this, see if I can get this feature. Like one of the great features is there's a lot of different places on the system where malware likes to put objects, like they like to execute objects out of. And so if you simply benign programs never put stuff or rarely put stuff, and you look at when they open up a file, you see, is it in one of these places? Okay, so then we'll create a feature, opened file in blacklisted directory, poof. But that set of blacklisted directories comes from understanding of what malware likes to do and what it doesn't like to do. So it's kind of like you have to understand the problem space in order to figure out what features you might want to extract. And then the other part is that some features are good for machine learning and some features aren't. And so I'll talk a little bit more about that in a second to show you an example of what kind of data machine learning likes and what kind of data machine learning doesn't like, doesn't help.
Can I ask a question? The training
Sure.
data?
Yeah.
What is the strategy for selecting training data? Like, are you picking known bads, known goods? Like, what is
Yeah, so that's, in the case of malicious data, it's really easy to get a lot of malicious samples. You go to VirusTotal, you can get millions of them. But you also need to have, like you said, a good set of benign samples. And you probably need more benign samples than you need malicious samples. And that turns out to be the biggest challenge, or one of the bigger challenges, is collecting a representative and large enough set of benign applications to test. So you need both benign and malicious, and the benign should be representative of the kinds of benigns that you're going to see out in the world. Because if you only collect, for example, a great source of benign samples is the Microsoft operating system itself. It has thousands of executables. If you look at your hard drive in the sys32 directory or a system directory, you just enumerate everything that's a P32, you get tons of files that way. But it's not very good for training here. So we thought, oh, it's the mother lode of benign samples. No, they're not representative because they all execute in a very unusual way compared to the kind of samples that you're going to see downloaded off the web, or they're going to be attached to emails. And so what we ended up doing was collecting samples from our customers themselves. Not actually the samples, because that violates the privacy, but I'll tell you what we did collect is after detonating a sample and creating this vector that represents the behaviors of the sample, what we could do is we could upload this data, not the sample itself, just this data, and that's good enough. And I'll explain why. Because that's what you train on. So once you have this vector, that's the machine learning models train on. And so we were able to collect the behavioral indicators from the sample, which is completely obfuscated in terms of what the program is and what it does. There's no way to reverse it and go back to anything that might be revealing, and you can actually train on that. So yeah, so training data is really important. In this case, getting malware is easy. Getting a good set of benign files is not easy, but you need a great representative sample of both. Otherwise, your classifier is going to get the wrong idea of what the world is like, right?
So, one more question here.
Yeah.
Because you're using behavioral detection and then using training sets, would be supervised learning then?
Thank you.
You might want to repeat the question.
Yes, so this would be supervised learning. What's the machine learning toolkit? There's really two different kinds. There's supervised learning and unsupervised learning. There's also, you can always mix and match them, and so you can create a category of semi-supervised learning, but let's just stick to these two categories: supervised learning, unsupervised learning.
And behavioral detection can be applied to both?
Yes. Yeah. So what's supervised learning? Supervised learning is when you have a set of samples and the outcome of each sample is known. You know ahead of time whether it's benign or malicious, for example. And you train with that additional knowledge of this sample is benign, this sample is malicious. And the training techniques, there's a lot of them. I've listed a few that I'm familiar with. Logistic regression, support vector machines, classification trees, random forests, that's all example of classification trees, and neural networks is another example of training techniques used for machine learning for supervised learning. XGBoost is a great classification tree algorithm. It's one of the most popular right now, one of the most effective classification techniques. It was an algorithm that was optimized recently in the last few years, and it's just proven to be super effective. Neural networks, deep learning, that's what all the stuff that Google Translate, image recognition, all that stuff is using deep learning as the fundamental advance there. So how does supervised learning work? You start with your training data, and you get features for each sample, that vector. But you also add another bit, which is which class does it belong to. Then you train the model, and this could take quite a while, depending on the number of samples and the training technique that you have. Like, for example, to do a random forest on a set of 100,000 samples, half of them benign, half of them malicious, with in the order of 1,000 features, could take maybe 8 hours to complete on, a multi-core system. It's chunked through and then what you do, once you've got that model, then you get a new sample, you extract the features out of it, the same way you extract the features for everything else, but in this case you don't know the determination. Then you give that to the model that you just created, and it will give you a probability of whether it was in the one category or in the other category. And typically the application of the model is almost instantaneous. It's very quick. Depending on the type, it's a little slight variation, but it's done in milliseconds, at most maybe a second in some cases. And then you get your determination, and typically you get a probability. And so some number between 0 and 1, greater than 0.5, and equal to 0.5, it's one category less than it's in the other category. So that's the basic approach for supervised learning. So let's take a look at a couple of these techniques, compare, see what the differences are, so you can get an idea of what does it really mean to have these different kinds of training techniques, like model types. It's like different kinds of cars. They're good for different purposes, like a Jeep. It's good for one thing. Minivan, it's good for something else. And so you'll buy a different kind of car depending on your application. Same thing for these models. So a linear regression technique is basically draw a line or a plane, figure out a plane that minimizes the error of the classification. So here's an example of the line that would minimize the error. There's the fewest dots on the wrong side of the line in this case. That's the line that minimizes that error. And so logistic regression is a way of figuring out where that line needs to be. Now a decision tree can look at the value and say, wait a second, everything that has a y value greater than this top line, that should be bad. Okay, let's just cut it off there. Those are bad. Okay, now, the remaining set, what do I do? Well, if it's below this line, then let's separate that group out a little bit as well, and then we can divide out the x-axis between these two values, and if it's between these two values, then it's over there. So you can see you can actually create arbitrary rectangles with a decision tree, slicing and dicing it so that you can pare down your separation boundary. It's not linear, it's not really, there's no function that defines this, but this is the representation of how a decision tree would work. And in this data set, the decision tree is much more effective because it can draw a nice little box around the two categories. So it seems like, yeah, decision trees are great, except for if you get a data set that looks like this, where the separation is really best described as a line, and there's some on the wrong side, but the decision tree goes crazy. Here it says, oh, wait a second, I see these couple of points here. Let me draw a little box around those guys. Oh, here's one. Draw a box around those. There's one. Let's draw a box right around this guy. And so you get this, it's trying to minimize the error, and it's really good at minimizing the error, so it can draw all these boxes, but this is what's a great example of an overtrained sample or overfit model, where it's really not generalized, the solution, because these dots, that dot might have just moved a little bit over to the side in real life, and now it's misclassified. It's really, probably there's error in your data, right? There's a concept called the irreducible error of your data. And for example, if you're trying to classify screws, that you would use to screw in a shelf or something like that, they all have different thread depths, right? There's these really big gauge screws and fine gauge screws. And so you might want to classify the screws by their length and also by their thread and their width. But if you're measuring the thread and all you have is a regular old ruler that can go to like a 30 or 16th, you can't then use that data to distinguish between screws that have a thread difference of less than a 16th, because your observation accuracy is only to the 16th of an inch, and these threads might differ based on a 32nd or a 64th, if you get some of those fine. So there's no way you can really distinguish between certain subclasses of screws with that data set. So there's a certain amount of error that you're going to have in any classification you do. Every data set has in some irreducible error where you just don't have enough granularity to be able to distinguish. And so your model is going to basically be stuck with that error. And what you don't want to have is you don't want to have your model trying to take into account this data error observation problem and try to make some conclusions based on it. And so that's really what overfitting translates into, is to try to make distinctions where they're not applicable. And so that's why it's important to understand your data set and what the strengths and weaknesses of certain kinds of models are with respect to that data set. And that's where really a data scientist helps out, because that's, you study all these different models, you study all the pros and cons, and then you understand how to apply them and when to apply them. So while we're on the topic of different models, let me take a little tangent and talk about deep learning a little bit. I haven't used deep learning myself, but it's a really popular term. And there's a great misconception associated with it with a large percentage, I think, of folks. And deep learning doesn't mean deep understanding. You know, people get all scared, oh, they've got this deep learning. That means I'm not going to be out of a job next year, for sure. It doesn't mean that at all. The deep in deep learning doesn't mean deep understanding. What it means is this: deep learners are neural networks. And in the 80s and 90s, most neural networks are defined as having an input layer, an output layer, which could have an arbitrary number of nodes, and then one or two hidden layers. And each of these layers take the inputs from all the layers previous, do some calculation, and generate a signal on the output. And so the problem is trying to figure out what the weights are on each one of these nodes. That's a regression problem. It takes a bunch of computation, and up until maybe 10 years ago, maybe 8 years ago, people really couldn't do the computation for more than two hidden layers. All of a sudden, in the last 10 years, people figured out how to solve this problem using MapReduce kinds of techniques on the massive kind of infrastructure that Google has deployed, split up the problem. They were able to solve the optimization problem for more than two layers. And so the deep refers to how many layers deep is your neural network. It turns out that they can solve some really interesting problems with that. But that's what deep learning is about, is a neural network where it's got more than two hidden layers. So let's take a specific example of model generation in the JTP detection case. So what we do is we take a sample and we run it in our sandbox. And what we get output from that is a trace file. And the trace file is what system calls did it make. It's called create file. It's called NT system query information with certain arguments. It's called alloc memory. It's called blah, 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 blah. And we get maybe between 10 and 1,000 or 10,000 trace lines. And each trace line, or each combination of trace lines, we translate into features. We create that feature vector. And this is where the art comes in, where the knowledge of how sequences of calls could be interesting. Like sometimes when they create a file in a temp directory, what they'll do is they'll actually create it somewhere else, and then they'll move it, because they know detection solutions are looking for the call to create the file in that directory, so they'll try some backdoor way of doing it. So you build a system to catch that as well. So there's a lot of art in coming up with that trace vector. And then that feature vector, you then run a model generation algorithm on. We've gone through a whole bunch of them. Currently we're using random forests. It generates a model, and then we deploy those models in our product, so that when we get a new sample, we sandbox it, extract the features. Sandboxing takes some amount of time. Extracting features is almost instantaneous. Applying the model is almost instantaneous. And then we get a result. And we have a different model for every different file type, because they all exhibit different behaviors. Like there's a model for EXEs, there's a model for PDFs, there's a model for doc files, and that's what we deploy. Question?
So in generating those traces, do you actually execute the code concalically to actually get the different execution paths to exhibit the behaviors that you have in your feature vectors?
Yeah, I didn't quite hear what you said. Do we execute the code?
Concomitantly, do you actually execute both symbolically and concretely to get it to actually exhibit?
Yeah, no, we just spin up a virtual instance of Windows, and we say poof, and we run it like it was clicked. And we run it, we hook it, using a trampoline hook, so that we can basically intercept every single system call, get all the arguments, and we write that out to a file. It's like strace or ktrace under Linux. Windows doesn't have that, so you build your own system for doing that. And we actually typically detonate it with a live internet connection too. So that if it reaches out, it goes and gets stuff and pulls down other stuff. And we trace all those things too, so that everything that gets spawned from that process gets traced.
And during the course of that execution, it could actually be making checks along the way if it's actually found something of interest. What I'm saying is, do you actually explore all of those paths?
Yeah, I'm not quite sure I understand your question, but we execute the process completely, and we follow all the other processes that it executes. If it injects itself into another system process, we'll trace that as well. And so we'll gather the traces for all of that. And that we'll consider that a single trace file, and then we'll extract features on everything that we just collected. So it's like running ktrace if you're familiar with Linux or BSD, you run ktrace on a program, you see all the system calls, all the arguments, everything like that. So it's a high level, it's not an assembly language view, it's a system call view of the behaviors, which is a higher level of abstraction. It'd be interesting to go to a lower level of abstraction to see other things you could extract other kinds of features from. So that's supervised learning. That's what we do. And it generalizes quite well. We can catch a lot of malware that way that's brand new. Unsupervised learning is training it when the outcome of the sample isn't known. And some examples of unsupervised learning are clustering algorithms, where you try to group points together based on their proximity to one another. There's a bunch of different clustering algorithms. There's a way of looking at what are the features that are most important in distinguishing these things. That's principal component analysis. There's some other things. This is not an area where I have a tremendous amount of insight or experience. Take the training data, just have the features, that's all you have. You train the model. And then what you can do with that model is you can take the sample and figure which group it fits in, for example. Is it one of these, one of those, or one of these others? And that's a good way for the malware problem domain, figuring out what kind of malware are you trying to deal with. We haven't had a lot of success with this. In other words, the error rates are a lot higher than the error rates for supervised learning in our problem domain. So the signal we get out of that about in terms of malware category isn't as robust, let's say. So here's an example of clustering algorithms where you're trying to group them together by proximity. A couple of different kinds of techniques shown here. This is fuzzy clustering versus nearest neighbor clustering. The problem with clustering is that things break down in higher dimensions because as you add a dimension, the space between the points grows exponentially. And so if you have enough dimensions, every point is almost as equidistant from each other. The differences between the points start disappearing unless you have a lot of points. So every time you add a dimension, you have to add exponentially more points to still get decent clustering. So that's called the curse of dimensionality. So what you have to do is you have to cluster it based on a subset of the first do principal component analysis to select a subset of the features so you don't have too many dimensions so you can still cluster and get a valuable piece of data. So that's why that limits, in some cases, the effectiveness of clustering because you need so much data as your number of features increases. Supervised learning does not suffer from this, though, which is why it's so pragmatic to apply in real-life situations. These techniques that we talked about in terms of linear regression and decision trees, they can handle thousands of millions of data points thousands, hundreds of thousands, even millions of features, and you can still compute and get a decent model out in a reasonable amount of time, in hours or days of compute time. So that's why supervised learning is one that you'll find more often in practical applications. The curse is the curse of dimensionality. It's that if you're going to do unsupervised learning and clustering, as you add features, you need to exponentially add the number of data points that you have. And to the question earlier, collecting enough data, getting enough malware and benign samples turns out to be pretty difficult. So we can collect maybe on the order of tens of thousands or maybe hundreds of thousands of samples. Collecting beyond that, in terms of benign data, is difficult. And so that limits the amount of clustering you can do, because if you put that in a, in a 50-dimensional space, those points are going to be so far apart from each other, it's going to be hard to find any clusters. So this is an example. Question?
How do you know that the supervised learning is not sensitive to the curse? Is this an experimental thing, or is there some theoretical basis?
Yeah, no, it's math. It's the basic math. You don't have to worry about dimensionality, because just the way the algorithms work. They'll just use the points that are there because the values that are there, I'm not sure if I can explain it any better than that, but the algorithms are basically, you can still find a plane to separate the points, and no matter how many dimensions, right? If there is a separation, you'll still be able to find it. You don't need more points in order to find that plane. Even if it's really sparse, you'll still be able to find this big open space where you can put a plane in between and separate the points. Whereas if you try to cluster it, everything's really far apart. There's no clusters. Everything's too far apart. Sort of the intuitive understanding of that. So it's important to understand your data, because if you do a linear regression across a data set without having looked at it first, you might draw a line that looks like this. But if you cluster it first and then do linear regression, the actual separation might be a lot different once you've clustered your data. So understanding your data and what it looks like is important. So sometimes these clustering techniques are good for just examining the structure of your data to see what kinds of techniques you should apply to try to get the correct level of separation. All right, so the last thing I really want to mention about this is the signal-to-noise ratio. When you apply these things in theory, you're going to get a number out of your model, which says, what's your detection rate and what's your false positive rate? How much are you going to catch, and how many mistakes are you going to make? And in practice, I've seen a lot of papers that say, in our false positive rate, we detected 70%, and our false positive rate was only 11. And they're really happy to publish a paper, somebody gets a PhD. In practice, in security, every false positive is a signal that some poor schmuck has to look at, a line in their inbox saying, something happened, take a look at this. And so they have to go and do some work. So a false positive rate of 11% might not be so great. But here's the other key part that a lot of folks don't think about, and that is that how frequently does this thing that you're trying to detect actually occur in practice? Because even if you have a 1% false positive rate, which from a research point of view would get you 2 PhDs, because it's such a great number, great result to have, in practice, we had our best classifier was 98% detection rate, 0.02% false positive rate. It's great. Can't use it. We could use it up until sometime in 2014. It was a PDF detector. Did awesome. All of a sudden, the PDF malware landscape changed. It used to have 1 in 1,000 was bad. All of a sudden, it went to 1 in 100,000 was bad. That same classifier all of a sudden swamped the SOC, the Security Operations Center. And this is why. if you have a situation where the event is 1 out of every 100,000, and you build a classifier that's got a 1% false positive rate, can detect 94% of the samples, that means you're going to get 1 false positive every 1,000 samples. Right? So if you've seen 100,000 samples, you're going to have 100 false positives, 1,000 false positives. And how many detections will you have? 1. So is a security operations center analyst going to pay attention to your solution? No. They're not going to pay attention to your solution. If you have a 0.1% false positive rate, it's 1 in 100. If you have a 0.01, it's 1 in 10. They're still not going to look at it, because they're going to have to look through 10 things that are bad before they get to the thing that's good, and that's way too much work. Because every time they have to call up somebody and say, hey, did you download this PDF? Yeah, can I take a look at it? No, not right now. Well, I have to come by and grab your laptop. Is that okay? No? Okay, I'll come back tomorrow. And they got 10 of those to do before they get one. Oh, that's a bad one. Oh, this is just some receipt for something. So really, operationally, the false discovery rate is in a very important number. So just what they call the confusion matrix, which is how the data scientists like to look at the effectiveness of the model, where they have the 4 numbers that define the detection rate, the true positive, false negative, true negative. That's not as important as the false discovery rate, which depends also on the frequency of the occurrence in your sample set. And that really gives you the number, which is what's the percentage of signals that are going to be bad? If it's over 50%, you're probably going to tire out whoever's looking at that signal from an operational point of view. If it's a 1-to-1, you might still be motivated to look at one, because every other one is going to be, all right, I missed that one, but that one's a good one, right? You get that hit, oh, I found something bad. But if it's like 3-to-1, 3 bad for every one, they'll probably start getting tired. So that's what we found. We're trying to get a 50% false discovery rate or less. And so that depends then on the frequency of the event that you're trying to detect. The less frequent it is, the much harder it is to get a machine learning classifier to actually detect it, because getting a classifier that does better than a 1% false positive rate is hard in this problem domain, in my experience. So then what you do is all kinds of tricks. You get a 1% classifier, you get that signal, and then you try to filter out the bads using some other technique. Like one technique we look at is we look at how has this piece of malware, has this hash been seen out in the world before? Has anyone ever seen it? And when's the first time they saw it? If it's been out in the world for more than a month, and we have a static engine that says it's clean and we say it's benign, then we'll say, oh, we'll believe the static. Because the static engine's good on older stuff, and so we'll trust it on stuff that's over a month old. But if it's new and it conflicts, then we'll trust us, you see? And so that can cut out a ton of false positives. So then you use all those kinds of tricks. Then domain-specific knowledge and other tricks to reduce the false positive rate to make this stuff operational, because the person who has to respond to this signal has to fit within a normal workflow that somebody can manage. All right. So what are the takeaways? In my opinion, when done correctly, machine learning can maximize threat detection. And it's a really efficient way of getting high quality detection. We were able to, with a team of like 3 people, we were able to get detection that was on par with some really heavyweight companies with teams of hundreds doing the same thing. And that's simply the power of machine learning. Once you get the data to the machine learning engine, you push a button and it does all the work for you. You can detect stuff, it generalizes well. From this detection perspective, you can detect stuff that you don't even know, that you really couldn't imagine a way to detect any other way. A lot of times we get a detection, we have no clue as to why, and that's one of the shortcomings. A lot of techniques you can't reverse and explain to someone, this is why it got detected. We can just say, well, it got detected. Sometimes you see just 8 traces. You only have 8 trace lines. The thing says that's malware, and you go, is it? How can you tell? And yeah, it is. More likely than not, it's malware. Why? You don't really know. There's some non-determinism that way. The other thing you can't do is you can't build a machine learning classifier and guarantee detection of a particular sample. If you want to guarantee that WannaCry gets detected, machine learning is not for you. You can just put it in a data set, and if WannaCry sample looks like enough other malware, chances are it's going to catch it. But if it happens to be an outlier, there's no way really to tweak the machine learning engine to say, you do that set and that one, please. You can't do that.
So, quick question.
Yeah.
So does that mean every time you identify a new domain, you must create a new model?
Yes. You get a new data set, new set of features, build a new model.
Okay.
So you want to have someone who's got experience with the data science part, applying machine learning, and you want somebody who understands the domain. What are things that are likely to help detect or not detect that particular area? So subject matter expertise is important.
Okay.
You mentioned landscape changing. What's the frequency that in the same domain you have to alter it because somebody's trying to find that threshold, that plane that you developed, they found it and they're sneaking in underneath it. How often does that happen?
Well, what we find more is that some external event happens in the landscape, suddenly shifts so that the frequencies change. Like all of a sudden, I think 2 years ago, the Russian police rolled up the criminal group that was responsible for the Angler exploit kit. And it turns out they're responsible for a bunch of other exploit kits too. And all of a sudden, that landscape just changed. From one day to the next, boom, web exploits just fell off the map. All of a sudden, a crypto ransomware started coming up like 2 years ago. All of a sudden, poof, in a matter of 2 months, that popped up, completely different tradecraft, so now you have to design something to catch that kind of malware. Because it might be different kinds of behaviors. Then you go back to your domain expertise and say, what is it doing differently? Well, let's add some new features to look at the behaviors that we know that exhibits and see if we can differentiate that way. So we're typically building new models every 3 months. It's a really scalable way of detecting zero-day malware. Know your data is probably one of the most important things. Know the benefits and pitfalls of your algorithms, and be ready to rinse, repeat. Just try it again. That didn't work. Okay, what else can we throw in there? Great example of rinse and repeat. Kind of armoring that you start to see in malware is try to avoid sandbox detection. They know you're running it for a certain amount of time, for like a couple minutes. So what they'll do is they'll just delay, not do anything bad for those first couple minutes because they figure sandbox is going to give up. In real life, you got a couple minutes. Who cares? So what they would do is they do a sleep call. Long sleep, but the very first thing they would do is sleep. So we added a feature if they do a sleep at the beginning. We'll catch that stuff. So then they got smart and said, well, let's not do a sleep. Let's do a whole bunch of little sleeps. And so then we wrote a feature for catching a whole bunch of little sleeps. Let's do cumulative sleep. Caught that stuff. And so they said, well, let's not use sleep. Let's just call a function over and over in a loop and burn CPU. They don't want to actually burn CPU in a tight loop because that will make the system unusable because it's consuming all the CPU. But what they'll do is make a system call, and then that system call is an error code because that doesn't succeed. And that takes a lot of time just doing a system call, and they can burn clock without burning CPU. And so we saw these patterns all of a sudden of the same system call over and over and over and over again. So then it was a create file call. So then I thought, I'm smart. I'll put a counter for create file and add that to the feature set. Great, caught that example of malware. But then they decided to use a different function, create new text. So I got you. I'll do one for create new text. Poof. And then there was another function was I can't just, it's like whack-a-mole. I can't just keep on adding features for every system call. So what then I did is for every system call that was made anywhere in the program, I would also add a feature that was just the count of how many times that system call was made. So that way it was covered, except it didn't budge the detection number. It's like, what? So then what I did was I added, rather than the absolute count, I added the percentage instead. Instead of it was 10 calls, it says what percentage out of the total number of calls that was made to everything was this. All of a sudden, the detection improved. And so that's understanding a little bit about how machine learning likes to look at data. Because if you've got a sample that's executing 100 times, or a sample that's executing 10,000 times, 10,000 rows, this one's going to have a count of maybe 80 create files, and it's burning a loop, where in this one, it might just do 80 normally because it's just executing normally, right? Because it's got 100,000 entries, 80 calls to create file is not unusual. And so, but here, if the percentage, I gave the percentage here, the percentage of create file would be 80%, whereas here, the percentage would be point something percent. So all of a sudden, you can see it's really the percentage of calls that was important, not the total number of calls. And because of the way the data gets distributed out, you need to normalize it so the machine learning can compare these two different kinds of execution. One that executes a lot and one that executes a little still now are level set so that it can be made a comparison and they can use to discriminate between the two features. So that's know your data, be ready to rinse and repeat. And so, just a summary, machine learning is really discovering statistical relationships with data. It can be big data, it can be small data. I mean, because we're doing hundreds of thousands of samples, that's not really considered big data. But the most important thing is relevant data. Get the relevant data, and this stuff can really do some amazing discrimination for you. Distinction. Well, thanks so much. I think I kept you a few minutes over. If you have any questions, otherwise, I really appreciate your time. Thanks so much.